Now they have to prove that these aren't extraterrestrial. And they also move without creating an exhaust or breaking the sound barrier. They didn't specify what other was, but you can fill in the dots yourself.
Avi Loeb has just sounded the alarm about 3I/ATLAS, claiming it's even more dangerous than the baffling Oumuamua, and what he's suggesting might keep you up at night.
That was just the night over which it was realized by a few amateur astronomers that indeed the Atlas survey, that's a telescope of half a meter, which by coincidence discovered the third interstellar object, 3I Atlas. The reason it's an interesting coincidence is because during the same time, the Rubin Observatory, which is roughly the same place in Chile, they are neighboring each other, was inaugurated. This small telescope that is only half a meter, whereas Rubin is 8.3 meters in diameter. So this small telescope discovered an interstellar object. Now Rubin can follow up on it and see it as well. Why did it discover this tiny telescope? This object is 4.5 times the Earth-Sun separation in terms of distance. The reason is it's very bright for its distance. In fact, if you assume that it's a solid object, like an asteroid, a rock, then it has to be 20 kilometers in diameter. And that's twice as large as the asteroid that killed the non-avian dinosaurs. Just think about it. Such an asteroid hits the Earth once every 66 million years. We get impacts by asteroids the size of a meter or so every year. So there are many more small objects than big objects. And the minute I realized that, the same morning, when I realized, oh, this one is so bright, I calculated the size 20 kilometers. I said, this makes no sense because there are a million objects the size of Oumuamua, tens of meters, for every object that is 20 kilometers in diameter in the main asteroid belt of the solar system. So I said, we haven't discovered a million Oumuamuas before we discovered this one. How come it's so big?
This gigantic interstellar object is tearing through our solar system with moves that defy every textbook explanation. It's not just moving fast, it's moving smart, like it's being guided. Some scientists whisper it could be artificial, the first true sign that someone or something out there knows we exist. Could 3I/ATLAS be an alien probe? Or is it carrying something far worse? Join us as we find out why Avi Loeb thinks 3I/ATLAS is more dangerous than Oumuamua. Something is watching us. Astronomers discovered something disturbing on July 1st, 2025. A small telescope in Chile spotted an object moving through space in ways that break the basic rules of physics. Scientists named it 3I/ATLAS, making it only the third confirmed visitor from outside our solar system. The object presents an immediate problem. Its brightness suggests it measures roughly 20 kilometers across. This size would make it twice as large as the asteroid that killed the dinosaurs 66 million years ago. Such massive space rocks should be incredibly rare in the emptiness between stars. Professor Avi Loeb at Harvard calculated the odds. For 3I/ATLAS to exist as a natural asteroid, interstellar space would need to contain more rocky material per cubic meter than all the metals in the entire Milky Way galaxy. The mathematics simply refuse to work. Astronomers should have found a million smaller objects before discovering something this enormous. The timing raises additional concerns. 3I/ATLAS entered the outer boundary of our solar system approximately 8,000 years ago. This date coincides precisely with when humans began recording their history on Earth. Ancient civilizations started documenting events, building monuments, and developing written language around the same period. This object began its journey toward our Sun. 8 specific orbital characteristics make 3I/ATLAS stand out from typical space debris. The object approaches from the direction of the galactic center, where thousands of stars create a crowded background that makes early detection nearly impossible. Its path follows a retrograde orbit, moving in the opposite direction to Earth's motion around the Sun while staying within the same orbital plane. The statistical probability of these orbital alignments occurring by chance measures 0.2%. Random objects from interstellar space should arrive from any direction with equal likelihood. 3 I/ATLAS chose the most strategically advantageous approach route. Its closest encounter with the Sun will occur on October 29, 2025. Earth will be positioned on the exact opposite side of the Sun during this approach. This timing creates what aerospace engineers call an eclipse situation, where the object remains hidden from Earth-based telescopes during its most active phase. The October timing serves another purpose. Objects moving at high speeds can use proximity to the Sun to perform what scientists call an Oumuamua maneuver. This technique allows spacecraft to gain or lose tremendous amounts of energy using minimal fuel by firing engines at the point of maximum velocity. Military strategists recognize this approach pattern. Fighter pilots in World War II always attacked with the Sun positioned behind them to avoid detection. The same principle applies to any object seeking to observe Earth while remaining hidden from our telescopes. 3 I/ATLAS will pass within striking distance of Mars, Venus, and Jupiter during its solar system transit. The probability of random timing that allows such close planetary encounters measures just 0.005%. From its projected position, simple ballistic trajectories could deliver payloads to any of these worlds using conventional rocket technology. Spectroscopic analysis reveals the object displays a reddish color, typical of surfaces exposed to cosmic radiation over long periods. However, no gas emissions characteristic of comets appear in the data. Traditional explanations for interstellar visitors fail to account for 3 I/ATLAS and its unusual properties. The dark forest hypothesis offers one possible explanation for these observations. This theory suggests advanced civilizations remain silent and hidden to avoid detection by potential predators in the galaxy. Such civilizations might send reconnaissance missions to monitor emerging technological species. Amateur astronomers with modest telescopes can observe 3 I/ATLAS until early October 2025, when it disappears behind the Sun. The surveillance mission might be just the beginning. But what if the physics of 3 I/ATLAS reveals technology that shouldn't exist? The impossible physics. The mathematical impossibility of 3 I/ATLAS becomes clear when examining its fundamental properties. Natural asteroids in interstellar space follow predictable size distributions. Small objects vastly outnumber large ones, following what astronomers call a power law relationship. For every asteroid measuring 20 kilometers across, roughly 1 million smaller objects should exist in the same region of space. Surveys conducted over the past decade have detected only 3 confirmed interstellar visitors. Oumuamua measured approximately 100 meters in length. Comet Borisov displayed typical dimensions for objects of its type. 3 I/Atlas breaks this pattern completely by appearing as a massive outlier without the expected population of smaller companions. The brightness calculations present additional challenges. Solid rocky surfaces reflect sunlight at known rates depending on their composition and texture. Dark carbonaceous materials reflect roughly 4% of incoming light. Metallic surfaces can reflect up to 60%. Even accounting for the most reflective possible composition, 3 I/ATLAS would need its reported diameter to achieve observed brightness levels at its current distance from the Sun. Thermal modeling reveals another inconsistency. objects traveling through interstellar space for millions of years reach equilibrium temperatures near absolute zero. When approaching a star, their surfaces heat up and begin radiating energy in predictable patterns. 3I/ATLAS shows thermal signatures that match its visible brightness, confirming the size estimates while deepening the mystery of its origin. The structural integrity of such a large object presents engineering challenges. Asteroids measuring more than a few kilometers across typically show signs of gravitational reshaping over cosmic timescales. Their irregular surfaces smooth out as weaker materials migrate toward gravitational equilibrium. 3. I/ATLAS maintains characteristics suggesting either recent formation or artificial construction designed to resist natural weathering processes. Spectroscopic data adds complexity to the puzzle. The reddish coloration indicates surface materials that have been exposed to cosmic radiation for extended periods. Organic molecules called tholins form when ultraviolet light and high-energy particles interact with carbon-containing compounds. This process requires thousands of years to produce observable color changes. The contradiction becomes apparent when considering travel times. An object originating from the nearest star system would require roughly 80,000 years to reach our solar system at typical interstellar velocities. Such lengthy exposure should produce much more pronounced surface alterations than currently observed on 31/ATLAS. Density measurements offer another avenue for investigation. Natural asteroids display densities ranging from 1.3 grams per cubic centimeter for loose rubble piles to 5.3 grams per cubic centimeter for solid metallic compositions. Gravitational perturbations during close planetary encounters can reveal density through precise tracking of trajectory changes. The absence of outgassing distinguishes 3I/ATLAS from typical comets, while raising questions about its composition. Volatile materials like water ice, carbon dioxide, and methane should sublimate when heated by solar radiation. Even trace amounts of these substances would produce detectable gas emissions and visible coma formation around the object. Advanced materials science suggests possible explanations for these anomalies. Synthetic composites could maintain structural integrity across vast distances while exhibiting thermal properties unlike natural minerals. Metamaterials designed for specific optical characteristics might explain the unusual brightness-to-size ratio observed in telescope data. Ground-based observatories continue monitoring 3I/ATLAS as it approaches perihelion. Radio telescopes search for artificial signals that might indicate technological origins. Space agencies evaluate mission concepts for close-range investigation, though the object's high velocity makes interception technically challenging with current propulsion systems. The October solar encounter will provide crucial observational data about the true nature of this mysterious visitor from interstellar space. The physics-defying nature of this object becomes secondary when considering what happens during its closest solar approach. But will humanity be ready for what October 29th might reveal? October 29th. The date. October 29th, 2025 represents more than just another astronomical event. 3I/ATLAS will reach perihelion, its closest point to the Sun, at precisely 0.39 astronomical units. This distance places the object well within the orbital path of Mercury, where solar radiation intensity increases by a factor of 7 compared to Earth's location. Ground-based telescopes will lose visual contact with 3I/ATLAS beginning October 1st due to solar glare interference. The object will remain hidden behind the Sun's brightness for nearly 4 weeks, creating what astronomers call a solar conjunction period. During this critical observational gap, the object will experience maximum thermal stress and potential activation of any dormant systems. the timing creates a perfect scenario for unobserved maneuvers. Spacecraft designers use perihelion passages to execute Oberth maneuvers, where engine burns at maximum velocity produce exponentially greater changes in trajectory. The technique allows missions to alter course dramatically while using minimal fuel reserves. 3I/ATLAS could theoretically change direction, deploy smaller objects, or modify its orbital parameters without detection from Earth. Solar heating effects on the object will peak during late October. Surface temperatures could reach 400 degrees Celsius, hot enough to sublimate water ice and other volatile compounds. Natural comets develop visible comas and tails during such thermal events as frozen materials transform directly into gas. The absence of outgassing signatures from 3I/ATLAS during its approach suggests either an unusual composition or artificial construction. Radio astronomy facilities worldwide have coordinated observation schedules for the October period. The Very Large Array in New Mexico, Arecibo Observatory successors, and the Square Kilometre Array precursor telescopes will monitor radio frequencies for potential artificial signals. The solar conjunction geometry actually enhances certain types of radio detection by using the Sun as a gravitational lens to amplify weak transmissions. Amateur astronomers face a narrow observation window before the object disappears into solar glare. Telescopes, with apertures as small as 6 inches, can track 3I/ATLAS through early October if equipped with appropriate solar filters and tracking systems. The object will appear as a moving point of light against background stars, potentially showing color variations that indicate surface composition or rotational properties. Orbital mechanics calculations reveal that 3I/ATLAS will pass within 0.12 astronomical units of Mars on October 3rd. This proximity represents the closest approach to any major planet during the object's solar system transit. Mars-based missions, including the Perseverance rover and various orbital platforms, could potentially detect the object using their scientific instruments if communication delays allow proper coordination. The European Space Agency has proposed emergency observation protocols using their solar monitoring spacecraft. The Solar Orbiter mission, positioned to study the Sun from various orbital perspectives, might maintain visual contact with 3I/ATLAS during periods when Earth-based telescopes cannot observe it. These spacecraft carry instruments designed to detect and analyze objects near the Sun. Gravitational perturbation measurements during the October passage will provide crucial data about the object's mass and internal structure. Precise tracking of 3I/ATLAS, as it interacts gravitationally with the Sun, could reveal whether its density matches expectations for natural rocky materials or suggest artificial construction with unusual mass distribution. The post-perihelion trajectory becomes visible again in November when 3I/ATLAS emerges from behind the Sun. Any changes in brightness, rotation period, or orbital parameters detected after the solar encounter would indicate active systems or structural modifications occurring during the unobserved period. December 2025 marks the final observation opportunity as 3I/ATLAS reaches its closest approach to Earth at 0.045 astronomical units before departing the solar system permanently. But what if the key to unlocking humanity's first cosmic conversation isn't human intelligence at all? What if our machines beat us to it? AI revolution will make first contact. The revolution already happening in astronomy labs around the world suggests artificial intelligence will likely serve as humanity's first ambassador to the stars. Modern telescopes generate more data in a single night than astronomers could analyze in decades. The Vera Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every 3 days. Each image contains billions of data points that could hide evidence of extraterrestrial technology. Machine learning algorithms now scan this astronomical data with precision no human eye could match. These systems identify patterns in light curves, orbital mechanics, and electromagnetic signatures that might indicate artificial origins. Unlike human observers who bring cognitive biases and preconceived notions about what alien technology should look like, AI systems approach each data point without assumptions. Recent advances in neural networks have transformed how scientists process signals from space. The Galileo project, established to search for evidence of extraterrestrial technology, relies heavily on artificial intelligence to distinguish between natural phenomena and potentially artificial objects. Their observatory systems in Massachusetts, Pennsylvania, and Nevada continuously monitor the skies using AI-powered analysis tools. The implications extend beyond simple detection. If an artificial intelligence system identifies genuine extraterrestrial technology, the same AI might serve as the initial communication interface. Advanced machine learning models could potentially decode alien signals or respond to technological artifacts in ways human minds cannot comprehend quickly enough. This technological shift reflects a broader change in how scientists approach the search for extraterrestrial intelligence. Traditional SETI programs focused on radio signals, assuming alien civilizations would deliberately broadcast their presence. Modern approaches recognize that extraterrestrial technology might be more subtle, embedded in the orbital characteristics of interstellar objects, the spectral signatures of distant worlds, or the electromagnetic emissions from advanced propulsion systems. The speed advantage of artificial intelligence becomes crucial when dealing with fast-moving interstellar visitors. Objects like 3I/ATLAS move through the solar system so quickly that human decision-making processes prove inadequate for real-time analysis. AI systems can process incoming data, identify anomalies, and even coordinate follow-up observations within milliseconds. Perhaps most significantly, AI systems might recognize forms of intelligence that operate on entirely different principles than human cognition. If extraterrestrial visitors use artificial intelligence for interstellar travel, as many scientists now consider likely, then machine-to-machine communication could prove more efficient than any human-mediated contact scenario. The integration of AI into astronomical research has already begun, revealing unexpected patterns in existing data. Algorithms trained on known astronomical phenomena occasionally flag observations that don't fit established categories. Some of these anomalies turn out to be instrumental errors or previously unknown natural processes. Others remain unexplained, creating a growing catalogue of cosmic mysteries that await further investigation. This technological revolution positions artificial intelligence as both the detector and potentially the first responder in humanity's search for cosmic neighbours. The question becomes whether our machines will recognize extraterrestrial intelligence before we do, and whether they'll know how to introduce us properly. While artificial intelligence prepares to become humanity's cosmic translator, a different revolution unfolds in boardrooms and private laboratories. But will traditional science accept help from unexpected sources? The billionaire space race against academic ignorance. The landscape of space exploration has shifted dramatically over the past decade. Private billionaires now fund astronomical research projects that universities once considered too speculative or risky. This transformation accelerated after traditional academic institutions repeatedly dismissed anomalous observations, leaving curious minds to seek funding elsewhere. Avi Loeb discovered this reality firsthand when mainstream astronomy rejected his interpretations of Oumuamua's unusual behavior. Instead of abandoning his research, wealthy individuals began approaching him directly. These benefactors offered something universities couldn't provide: freedom to pursue unconventional scientific questions without committee approval or peer pressure. The Galileo project emerged from this new funding model. Rather than relying on government grants or institutional support, the initiative operates entirely through private donations. This independence allows researchers to investigate phenomena that established astronomy departments actively avoid discussing. The project's 3 observatories represent millions in private investment dedicated to finding technological signatures in space. Silicon Valley entrepreneurs have proven particularly interested in extraterrestrial research. Many built their fortunes by recognizing patterns others missed or by developing technologies that seemed impossible just years earlier. These same individuals now see potential breakthroughs in astronomical questions that traditional scientists dismiss as fringe topics. The speed difference between private and academic funding creates striking contrasts. Universities require months or years to approve research proposals, conduct peer reviews, and allocate resources. Private benefactors can approve projects within weeks, sometimes days. When dealing with fast-moving interstellar objects like 3I/ATLAS, this timing advantage becomes crucial. Corporate research laboratories have also entered the field. Companies that developed advanced sensors for military applications now repurpose their technology for astronomical detection. These instruments often surpass university equipment in sensitivity and processing power. The same magnetic sensors used to detect submarines can identify unusual properties in space objects. Traditional academic resistance to these developments stems from multiple sources. Many established astronomers spent decades building careers around conventional interpretations of cosmic phenomena. Acknowledging that private researchers might discover something significant challenges their professional authority. Department funding also depends on maintaining credibility with grant-awarding agencies that prefer safe, predictable research topics. The generational divide compounds these tensions. Younger astronomers often embrace unconventional possibilities, while senior faculty members protect their reputations by avoiding controversial subjects. Private funding offers younger researchers alternative career paths that bypass traditional academic hierarchies. International competition adds another layer to this dynamic. Countries with less rigid academic structures may prove more willing to investigate anomalous objects. If China or other nations discover something significant about interstellar visitors, while Western universities debate funding protocols, the geopolitical implications could prove substantial. The democratization of space technology accelerates these trends. Advanced telescopes, once available only to major observatories, now cost less than luxury cars. Amateur astronomers regularly contribute observations that professional institutions miss or ignore. Sam Dean's discovery of 3I/ATLAS in archived telescope data demonstrates how dedicated individuals can make breakthrough contributions. This shift challenges fundamental assumptions about how scientific discoveries happen. The traditional model assumed that universities and government institutions would lead major breakthroughs. Private funding now enables alternative research paths that operate independently of academic approval. The question remains whether this new landscape will accelerate genuine discoveries or simply fund expensive speculation about cosmic visitors that may never materialize. Do you think AI will recognize alien intelligence before humans do, or are we giving machines too much credit? If 3I/ATLAS changes course after October 29th, should that be considered proof of artificial origin? Share your thoughts with us in the comments section. Remember to like, share, and subscribe for more. Also, click the next video showing on your screen. You will enjoy it.